Thanks for the introduction, and thank you for the invitation and organizing this great online seminar. Today, I'm going to talk about some inverse boundary value problems for a quasi-linear equation on a Lorentz manifold with boundary. This is a joint work with Professor Gunther Woman, and the results are based on the ones for nonlinear equations on Lorentz manifolds without boundary. So before we discuss the inverse boundary value problems, I'd like to overview some important previous results for the case without boundary. We consider semilinear or quasi-linear wave equations on Lorentz manifold. Suppose M is a one-dimensional manifold and J is a Lorentz metric with a signature minus plus plus plus. One example of the Lorentz manifold is the Minkowski space. For each point Q in the manifold, the tangent space, the tangent vector falls into three classes: the time-like vectors, the space-like vectors, and also the light-like vectors, and also the space-like vectors. We will say a curve is time-like if its tangent vector is time-like in the interval that we consider. We say a curve is causal if its tangent vector is time-like or light-like. The non-geodesics whose tangent vector is light-like are denoted by non-geodesics. The future light cone surface at the point X is a union of all future pointing non-geodesics starting from the point X. We say a point P chronologically precedes Q if there's a future pointing light curve from P to Q, and P causally precedes Q if there's a future pointing causal curve from P to Q. The chronological future is a set of all points Q that P chronologically precedes, and similarly we can define the chronologically past of the point Q. The causal future of a point P is a set of all points that P causally precedes, and similarly we can define the causal future of a point P. With these notations, so we can define the diamond set I of PQ, which is the intersection of the chronological future of the point P with the chronological past of the point Q. And similarly, we can define the causal diamond set J of PQ. In this talk, we consider Lorentz manifold, which are connected, time-oriented, and globally hyperbolic. We say a Lorentz manifold is time-oriented if we can choose the future light cone at each point in a continuous way. And the globally hyperbolic properties implies that there are no closed causal paths, so the time travel is prohibited. And also the causal diamond set is compact for all points PQ in M. Furthermore, we can, for globally hyperbolic Lorentz manifold, we can identify the manifold M with R for the time variable times a three-dimensional manifold N for the space variable. So the metric can be written as a suppose function minus a suppose function beta times dt squared plus kappa of ty. So here kappa of ty is a family of remaining matrix on the three-dimensional manifold N, which is mostly depends on T. So in this Lorentz manifold without boundary, we consider the following inverse problem. Suppose we have a time-like segment mu hat, so which is the vertical line of an observer. Let P minus and P plus be 2 points along this time-like curve. Basically, we can take P minus as the starting point, that as the point that we start the experiment, and we can regard P plus as the point where we end the experiment. Suppose we know a small neighborhood of this time-like segment, so which is called the observation set way, and consider a source f which is compacted in this set way. Let u solves the nonlinear wave equation. So we have Laplace the Bell-Trimming operator applied to u plus a u squared equals to the source. Before we have the source, u equal to 0. So here a is a smooth function which is non-vanishing. So for each small source f in way, this equation, this nonlinear equation, is well posed if the source is not small enough. So we could have we can have a solution. If we restrict the solution to the observation set, then this gives us the source to solution map. The question is knowing the observation set way and the metric layer, knowing the measurement, which is the source to solution map. So can they recover the metric J in this Lorentz manifold? In the paper by Korolev, Lassad, Woman in 2018, so this also show the data given by Wei and the source to solution map actually determines the conformal class of the metric up to diffeomorphisms for any point in the diamond set. Not only this, the topological structure and the differential structure are also determined, but in this talk, we only focus on the recovery of the metric. So here we consider the recovery in this diamond set because this is the maximum set that one can reach by a causal curve that starts from P minus and ends at P plus. And the conformal factor and diffeomorphisms here are natural abstraction, and there are counterexamples constructed in the paper by Lassos, Woman, and Wang in 2018. So this theorem is based on the result for the so-called passive observations. Basically, it says to recover the metric, one can recover the family of the earliest light observation set. So the light observation set for a point Q is the intersection of the light cone surface with the observation set way. The earliest light observation set is just a subset of this light observation set. This subset contains the points x such that there's no point y in the light observation set that y chronologically precedes x. That is, the set is contains all the points which is the earliest point in the light observation set. So this set has some nice properties. For example, its regular part is a three-dimensional submanifold. So even though we might have some caustics caused by the cut points in the light observation set, so the regular part of this one still has is still a smooth submanifold. With this theorem, so it suffices for us to recover the family of the light of the earliest light observation set for each point Q in the diamond set. There are many works, related works after this paper. One can consider some some nonlinear equations which has applications in physics or geophysics. For example, the Einstein equations, Maxwell equations in vacuum. And there are also some works that considers the recovery of nonlinear terms of given a metric using Gaussian beams. So today we will focus on the related works for inverse boundary value problems. So here I only listed the works related to nonlinear hyperbolic equations. I'd like to apologize if I missed some of them. So to prove the theorem, we are going to use microlocal methods. What is microlocal analysis? So the following two slides is going to serve as a quick introduction to microlocal analysis if this is new to you. But I know in the audience there are many experts in this area. Roughly speaking, microlocal analysis studies distributions, which is the generalized functions from a phase space point of view. So the tools we use in microlocal analysis include, but not limited to, pseudo-differential operators, Fourier integral operators, so which are operators whose Schwarz kernel are Lagrangian distributions. So basically, for Lagrangian distributions, one can expect the singularities are contained in a Lagrangian submanifold. And we also consider operators whose Schwarz kernel are paired Lagrangian distributions. So these are distributions, the singularities are contained in in a pair of intersecting Lagrangian submanifolds. For example, the solution operator to the homogeneous wave equation with initial data is a Fourier integral operator, and so its Schwarz kernel is a Lagrangian distribution, and the solution operator to the homogeneous wave equation with zero initial data has the Schwarz kernel that are paired Lagrangian distributions. So these tools are used to characterize the singularities of the solutions to partial differential equations, and we can also analyze the strengths of these singularities. So what are singularities? Basically, one simple example of singularities is they are the covector. They are the covectors where a function or a distribution has a jump at the point x and in the direction cosine. So here by jump, we mean f is not smooth. For example, consider this Heaviside function. So f equals to 1 in this lower half plane and equals 0 in the upper half plane. So for this Heaviside function, all the jumps happens along the x-axis in the direction that is parallel to the y-axis. So the singularities are covectors like this. So this Heaviside function is one example of the conormal distribution, which are distributions whose singularities are contained in a conormal bundle. Mathematically, we can use this Fourier transform to define the singularities, and the set of all singularities is contained in the wavefront set. So in the following, we are going to use singularities and their strengths to recover some features in inverse problems. The strengths of the singularities can be described by the principal symbol of a conormal distribution or a Lagrangian distribution. So the main idea to prove the theorem in this paper is to use linearization and the interaction of these totem plane waves to produce some new singularities. So we can recover the earliest light observation set. So recall for this, we have this nonlinear equation, and the input is a small source supported in wave, and output is a solution restricted to the observation set wave. So the difficulty here is we do not know how to solve this nonlinear equation explicitly, so we're going to use linearization to extract some information from the measurement. So first we know the linear problem. So the wave operator has a parametrics Qj. So Qj is a microlocal solution operator such that the wave operator applied to Qjf equals to f itself plus a smooth edge. So here, since we only care about the singularities, so smooth functions are ignorable. With this parametrics, so we can rewrite this equation as u equals to v minus qj a u squared. So we can regard this one as a approximation formula for u, and we can plug in this formula into Excel iteratively, so we can get some asymptotic expansion of u in terms of v like this. If we choose the source f depends on some small parameters, epsilon 1, epsilon 2, and we choose Vj as the solution to the linear problem for the source fj, then the corresponding solution for the nonlinear equation has this asymptotic expansion, so it also depends on epsilon 1 and epsilon 2. If we differentiate these small parameters and set them equal to 0, then we will get minus 2 qj a v1 v2. So this is very helpful because we know the solutions to the linear problem and we can analyze them. So this is called the second order linearization. If we consider 3 small parameters or 4 small parameters, we will have the third order linearization and the fourth order linearization. So here I use these 2 terms as the model term for them. Next, so one can choose a special source f such that the singularities of the measurement here, because after use this linearization, so the measurement we have qj applied to the product of the solutions to linear wave equations. So we can choose special f such that the singularities of these measurements will give us the earliest light ablation set. So how do we do this? There are 3 steps. So first, we can construct some point source fj. So suppose we have a point xj and have a light vector psi j. So one can construct a point source fj at xj whose singularities are near the psi j. So we can do this by choose the delta function and multiply it by a cutoff pseudo differential operator. Then if we consider the solution to the linear wave equation for fj, then this vj will have singularities propagate near the non-geodesics starting from xj in the direction of psi j. So qj will have singularities near this non-geodesics. And we call Vj the distorted plane waves. Before the first cut point along this non-geodesics, Vj is a conormal distribution if we stay away from the source. Then we can analyze the product of these conormal distributions by using the calculus. We can characterize the singularities of this product. And then we can understand the singularities of these measurements. So from the singularities here, so one can expect to recover the earliest light ablation set. So it turns out, the fourth order linearization term will gives us some new singularities. Yeah, this is because for any point q in this diamond set, if we choose the 4 non-geodesics properly, so this non-geodesics intersect at q and satisfy some properties, then the distorted plane waves that propagate near these non-geodesics will produce a point source at q. So this point source have singularities in all directions, and they will, after apply the parametrics, so the singularities will propagate along the under the bi characteristics. So we will have the light cone surface of Q. So the interaction of this light cone surface with the observation set V is a light observation set, and we can determine the earliest light observation set from this part. And this is true for each Q in the diamond set, so one can determine the family of earliest light observation set. And by the result for passive observations, so this determines the conformal class of the metric up to diffeomorphisms. So this is the main idea to recover the metric from the source to solution map. So next, I'd like to discuss the inverse boundary value problems for a quasi-linear wave equation. So here we consider a globally hyperbolic Lorentzian manifold with boundary. We have some assumptions about the boundary, and I'm going to discuss this later on. Here we consider a quasi-linear wave equation given by the wave property plus a quadratic form w of xu, the gradient of u. So here w is a quadratic form in the third variable, and it depends on x and u smoothly. So we can assume it satisfies this Taylor expansion. So it equals to a quadratic form n naught plus u times another quadratic form plus u squared times m plus some high order terms in u squared. So this equation is called the quadratic derivative wave equation. And it can be regarded as a simplified model of wave map equations. So one can show this equation. So here we impose some Newman boundary condition, and we can show this is well posed if the boundary source f is small enough. So for each boundary source that is sufficiently small, so we can solve this equation and restrict this equation to the boundary. So we have the Newman to Dirichlet map. So the question is, can we determine the metric and also the quadratic terms from the ND map? Let's see some previous results. So this type of equation has been studied in the work by Wang and Zhou in 2019 in a Lorentz manifold without boundary. So they showed that if we assume n0 and n1 are non-forms and m is now none, then the sawtooth solution map will determine the conformal class of the metric of the different morphisms in the diamond set. So here we say a quadratic form n is none if it equal to 0 for any point and any like factors. So one can show any non-form is a linear combination of the Lorentz metric and an antisymmetric quadratic form. And also there are some previous results for inverse boundary value problems. The recovery of the nonlinear terms for the semilinear wave equation has been studied in the paper by Hans Ullmann Jay in 2021. So they assume the non-geodesics do not have cut points, then the ND map will determine these nonlinear coefficients. The same semilinear equation for the no boundary case, that is the recovery from the sawtooth solution map, is considered in the paper by Lasse Woman Wang in 2018. In another paper by Hans Ullmann Jay, they consider the semilinear equation with this nonlinear term au to the fourth power. So they assume the non-geodesics in the set we consider do not have conjugate points, then the Dirichlet-Newman map will determine the metric up to diffeomorphisms and the conformal factor. So the main idea is one can construct the boundary source that generate these total plane waves, and to recover the metric, so one can detect the singularities of the fourth order linearization on the boundary. So this gives us the boundary light evolution set. If there are no conjugate points, then the boundary light evolution set will determine the conformal structure of J after diffeomorphisms. This is proved by the paper of Hans and Gunther, Hans and Ruhlmann in 2019. So now let's come back to the inverse boundary value problems for quadratic derivative nonlinear equations. The main result in my joint work with Woman shows with exception that n0, n1 are non-forms and m is non-null. This is the same assumption in Wang and Zhou's paper. With this assumption, so the ND map will determine the conformal class of the metric up to diffeomorphisms. So here we consider the restriction, the determination of the metric in the set W, which is the union of all diamond sets of any 2 points on the boundary. So this is like the maximal set that one can reach by a castle curve that starts at the boundary and ends at the boundary. So in this paper, we actually consider a local version of determination. one can consider a small portion of the boundary by using the ND map restricted to this small portion, so one can determine the metric J in a corresponding set. Of course, this small portion should satisfy some assumptions. Then with the metric G, so we can recover the quadratic form N1 and Nm up to non-forms if one assume only N0 is a non-form. So here, we cannot expect to recover the non-forms because when computing the principal symbol, the non-forms will give us some vanishing terms in the principal symbol. So we use the extension and the earliest light efficient set to recover the metric. So we allow cut points or conjugate points. So the main idea is we have the following. We do the following steps. So first, we extend the Lorentz manifold to a larger manifold M tilde G tilde, which is also a globally hyperbolic Lorentz manifold, such that M tilde is a manifold without boundary, and M is contained in the interior of M tilde. Then we construct a virtual observation set V. So V is contained in M tilde Z minus M. So we are going to use this virtual observation set and the metric, the extended metric here, to recover the family of the earliest light efficient set by detecting singularities on the boundary using the ND map. Then we can use the result for passive observations in this paper. So this family of earliest light observation set will determine the conformal class of metric up to diffeomorphisms. So let me explain step two in details. So to recover the earliest light observation set, so we want to create a point source at any point Q in the set W as before. But here we need to use some information on the boundary. So first, one can show the linearized ND map, so which is also the ND map to the linear wave equation. It determines the jet of J and the length relation on the boundary. So here the jet of J means like the derivatives of J of any order on the boundary. So we can extend the Lorentz metric to J tilde outside the manifold M. And then for each point Q in W, we can find 4 proper non-geodesics such that they intersect at Q before the first cut points. And this non-geodesics has tangent vectors which are linearly independent at Q. So next, using this non-geodesics, so one can construct boundary sources that are corresponding to them. So here we use a virtual point source xj in a way to construct the boundary source fj. And these boundary sources will generate distorted plane waves vj as before. So notice here vj, they do not reflect on the boundary, but with the nice properties of the 4 non-geodesics. So vj will interact at the point Q, and they will produce a point source at Q. Then the singularities of this point source will propagate in any light-like directions. So they will come to the boundary and reflect at the boundary. So we are going to use the DN map to detect the singularities on the boundary. So and this will give us the light intersection of the light cone surface with the virtual light emission set if we use the extended metric. There might be cut points or conjugate points, but one can construct the surface of the earliest stable singularities, so which can be regarded as a candidate for the earliest light emission set. Then by using other informations that we derive from the ND map, we can determine the earliest light emission set for each point for each point Q in the diamond set in the set W. So then we can use the result for passive measurements. The main difficulty here is caused by the presence of the boundary. Recall, because in some terms of the linearization, so we have the solutions to the linear wave equation in a manifold with boundaries. So the singularities of the solution will propagate along generalized broken by characteristics. So in some bad cases, you might have some gliding rays. To avoid this, we can assume the boundary is strictly non-convex. This will imply that for any non-geodesics that hit the boundary from the inside of M, we will have these non-geodesics intersect the boundary transversely. So we only have the reflection of singularities. And strictly non-convex boundaries will also guarantee other nice properties. Another difficulty is caused by the cut point. Recall the distorted plane waves we construct normal distributions from the source if before the first cut point. So we would like to consider the interaction of these distorted plane waves only in the open set N, so which is the complement of the causal feature of the first cut point along each non-geodesics. So this is enough for our analysis because we can tell when we can avoid these cut points step by step by using the so-called layer stripping method, which is proposed in Kerlev, Lessas, and Woman's paper. So another difficulty we have is after the link from the first order linearization, so we have more complicated terms. And these terms involved with multiple reflection. So we have several terms in the fourth order linearization. For example, for this one, so we have the parametrics applied to the product of a conormal distribution with the distribution A3. So here A3 is given by the parametrics applied to the product of a conormal distribution with A2. A2 has this parametrics, so the singularities of A2 will propagate to the boundary and then reflect. So to analyze A3, so we need to analyze the product of conormal distributions with another distribution who has singularities reflected on boundary, so which will be complicated. So both the singularities of A2 and A3, they reflect on the boundary. So we want to avoid this complexity. So we consider the interaction of distorted plane waves in the open set R. So here we define R as a complement of the causal feature of the point where each non-geodesics leave the manifold for the first time. So it turns out this open set R can be determined by the first order linearization of the ND map because the ND map, the linearized ND map will determine the length relation on the boundary. And if the linearization term is simpler, for example, if we have a term like this, so then one do not need to consider this open set R. As we mentioned before, so we only consider the interaction of waves in this open set R and N because in the intersection of these two open sets, the distorted plane waves are conormal distributions, and we can avoid complexities caused by the reflection. And on the other hand, this set, in this intersection theta, it contains enough information to recover the earliest light observation set, because for any point Q in W, so one can find 4 proper non-geodesics such that they intersect at Q in this open set theta. And when this is true, one can show a dense subset of the earliest light observation set is contained in this theta. So if we focus on the analysis in this set theta, we won't miss any information. So in this set theta, recall Vj is a conormal distribution And if we consider the interaction of two waves, for example, a term given by this one, so this is the parametrics applied to the product of two conormal distributions. So the product is has singularities contained in the span of the two conormal bundles. If we apply the parametrics, then the singularities will be contained in the span of these two conormal bundles. And also we have the flow out under the broken by characteristics. But since we focus on the set R, so which is a complement of the causal feature of the first reflection point, so we do not have the reflection part. So there are no new singularities produced by the interaction of two waves. If we consider the interaction of three waves, for example, this term, the singularities of the product here, so this is a product of three conormal distributions, and their singularities is contained in the span of the three conormal bundles. If we apply the parametrics, so the singularities are contained in the span and also in the flow out under broken by characteristics. So there are new singularities produced on the intersection of K1, K2, K3. So here Kj is a smooth manifold, which is a small neighborhood of the non-geodesics gamma xj psi j. So there are new singularities produced on the intersection of K1, K2, K3. So this is a one-dimensional submanifold, and these new singularities will propagate and reflect on the boundary. But it turns out this part of singularities are corresponding to a set of Hausdorff dimension at most 2. If we consider the interaction of four waves, for example, this term, first we need to analyze the product of a conormal distribution with a distribution which might have reflection on the boundary. But since A2, so the distribution A2 do not have the reflection part. So even though we have the reflection part for A3, but it's still analyzable. So, and it turns out, so for this product, for these terms, we only have two parts of new singularities. So the first part are produced of some one-dimensional submanifold. So this is caused by the interaction of three distorted plane waves. They will propagate and reflect. So they're corresponding to a set of Hausdorff dimension at most 2. So and we call this part of singularities as 1. And the second part of new singularities are produced at the point Q. So Q is an intersecting point of the four non-geodesics. So this part of singularities will propagate and reflect, but they are corresponding to the light aversion set in way. So they contain a three-dimensional submanifold. So they correspond to a set which has Hausdorff dimension at most, at least 3. If we compare S1, S2, so S1 is relatively smaller than S2. So even though the Newman to Dirichlet map will detect these two parts of singularities, but we can still distinguish them by looking at the Hausdorff dimension. So we can use the second part of singularities to construct the surface of the earliest stable singularities, and then we can construct the earliest light aversion set for each point. So after we have determined the metric J, so one can look at the third order linearization and also the second order linearization. So these terms, the principal symbol of these terms on the boundary at the first intersection reflection point contains some information about about the quadratic terms here. So by comparing the principal symbol of these terms, so one can determine the quadratic terms N1 and M. Yeah, that's the main idea of the proof, and that's the end of my talk. So here are some references, and thank you so much for your attention.
Thank you very much, Jan, for the very, very interesting talk. Thank you very much. Are there any questions or comments, please? Please feel free to unmute yourself. Are there any questions or comments, please?
Hi, can I ask a quick question?
Please.
Nice talk, by the way. So you probably said that and I missed it. So what was the stable singularities that you mentioned earlier?
You mean the surface of earliest stable singularities?
So the surface earliest, yeah. What is the stable singularities? You probably mentioned it and I missed it. But,
yeah, I didn't put the explicit form here. So this is like a set we constructed from, so recall the singularities of the fourth order linearization will create some light cone surface. And if we pick the earliest one, the earliest singularities, so this will give us the surface of the earliest set of stable singularities. So this is not the earliest light observation set in general, because yeah, sometimes you might have some non-geodesics which do not intersect at one point. So if they do intersect at one point Q, so this is the earliest light observation set. So otherwise, we need to distinguish that situation. Yeah. That's the answer to the question.
I see. Thank you.
Thank you very much. Are there any other questions or comments, please? Okay, if not, thank you very much, Jan, for the very, very nice talk. Thank you very much, everyone, for coming. Thank you very much.